Hi, everyone. I'm Matt Reynolds from the Department of Electrical Engineering at the University of Washington. It's a pleasure to welcome our speaker today, Sam Burden. Sam earned the BS with honors in electrical engineering from the University of Washington in 2008. As an undergrad at UW, he worked with Eric Clavens in the Self-Organizing Systems Lab. He then went on to earn a PhD in electrical engineering and computer sciences at UC Berkeley, where he was an NSF graduate fellow. He spent 1 year at Berkeley as a postdoc. And we're very pleased to welcome him back. In fall of 2015, Sam returned to UWEE as an assistant professor. Sam is broadly interested in discovering and formalizing principles of sensorimotor control. Specifically, he focuses on applications in dynamic and dexterous robotics, neuromechanics, and human cyber-physical systems. In his spare time, he teaches robotics to students of all ages in K-12 classrooms, maker fairs, and campus events. So it's a pleasure to welcome Sam, and thank you very much for speaking to us.
Well, thanks very much, Matt, for the very warm introduction. It's a real pleasure to be back speaking in the EE Colloquium. As Matt said, this is kind of home for me in a lot of ways as an undergrad and then back here as a faculty member. And it's actually a real pleasure because the last time I spoke in this colloquium was my job talk, my interview. So now I'm significantly less stressed. I'm in much more comfortable clothes, less formal clothing. And I'm really happy to share with you. I thought what I would do is, rather than kind of recapitulate what I talked about 2 years ago, I mean, you can watch the video on YouTube, I thought I'd talk about new results that were from the last, I wanted to say year and a half, but in reality it's closer to almost 2 years since my interview talk. So what I'll be talking about are new techniques for predicting the dynamics of sensorimotor loops. And the leading off point for this topic is the observation that human interaction with the physical world is increasingly mediated by automation. So I put up a number of examples here. I'll just highlight a couple. I mean, we know that Tesla sent out a software update a few months ago, and now their automobiles can effectively drive themselves on highways and kind of straight roads and things like that. I'll show what happens in kind of bad situations with Tesla in a few slides. For a long time, planes have been assisting pilots not only during steady state flight, but also takeoff and landing to ensure safety and improve performance, fuel economy. Increasingly, doctors are relying on robots and other kinds of automation, for instance, to assist them with improving surgical outcomes, but in general, improving clinical outcomes kind of more broadly. And of course, robots play a big role in factories, helping workers improve productivity, precision, efficiency of assembly lines. And then what I think of as a really exciting future direction for this interaction between people and machines is the possibility that machines can be engineered to assist us either in health or disease. And so a couple of the really exciting examples I've highlighted here on the right side are in the lower right corner. Jan is a quadriplegic woman who's been able to use recently a brain-computer interface to control a robot arm to do one of her favorite activities, which is eat chocolate, or just perform other kinds of daily activities that she's been missing out on for years, decades. And then in the upper right corner, Steve Collins' lab at CMU showed that a purely passive mechanical assistive device could improve energy efficiency of human walking. I think this is actually a really remarkable scientific accomplishment because we've essentially evolved to walk. That's one of the kind of primary leading theories of why we are upright bipeds, is to be able to efficiently move around our world, track down prey, and things like that. And so any new technological trend needs jargon associated with it. Matt was kind enough to use my preferred jargon, the best term that me and my colleagues have come up with. As kind of a catch-all term, we describe these as being human cyber-physical systems. So there's some human, of course, in the loop. There's also cyber elements. By this we mean computational, perhaps networked, perhaps relying on data from the cloud or something like that. But at the core, this isn't people just being online on message boards. This is tied to the physical world with mechatronic devices that the person's interacting with. Now this is a very broad, I've highlighted, very broad set of disciplines. It'd be remarkable if I was giving you a talk on mathematical principles that applied equally well across this wide swath. And in fact, that's not the case. And so I would just want to be upfront about the canonical or the kind of exemplar of a human cyber-physical system that I will focus on in this talk, and that's kind of the focus of my research, is this problem of robotic teleoperation. This is a pretty common term. This field has been studied for a long time, and so I'm kind of taking a fresh look at this in some way, fresh look at an established discipline in some ways. And just to give you an overview, if you're not quite familiar with this term or with this setting, we're imagining a situation where a human is controlling a robot. So the robot's not fully autonomous, it's semi-autonomous in a sense. And the human has access to sensory feedback. This could be in the form of, a computer display or a 3D rendering, or it could be some kind of representation of accelerometer data or other kinds of data collected from the physical system. And the person is able to provide inputs, motor control inputs to the robot. And these could be from literally like a joystick, like a PlayStation gamepad or something like that. Or it could be through more sophisticated, either like a brain-computer interface or a haptic interface where the person's directly giving and receiving force feedback. And what I want to highlight and focus on are the potential applications that this robot teleoperation could have. And so when I reflect on this, the thing that I keep coming back to is the idea that there are a lot of situations where we have humans doing jobs that are dull, dirty, or dangerous, and it would really be ideal if we could just remove the person directly from harm's way and replace their physical presence with a robot. So the example I think that's particularly relevant being from the Pacific Northwest and seeing the disastrous sequence of wildfires we had last year. This is a photo taken from one of the fires that actually ended up claiming the lives of a couple of first responders. I think it's kind of clear that ideally, when there's a fire or natural disaster, right now the best solution society's come up with is to put more people into that situation, take highly trained, highly skilled individuals and put them directly in harm's way and create the potential that they themselves could be injured or kind of subject to this disaster. But I think it'd be ideal if they could just be physically removed from that circumstance and remotely control a robot to fight the fires. And so in kind of reflecting on this and taking this argument to its logical extreme, one might imagine, well, why do you even want a person involved at all? Why not just build autonomous robots that can go and fight the fires on their own, and humans can just kind of watch the result of that on some display or something? So what I want to do is show a video of results from a recent robotics challenge. If you're not familiar with this, this was the DARPA Robotics Challenge, and so in which a collection of several dozen teams of researchers from leading universities around the world competed for millions of dollars in prize money. And yet this is kind of, well, I wouldn't say this is the best they could do. This is, of course, the blooper reel, and I'm going to show the real results toward the end of the talk. But I think this highlights that even with all of the talent and all of the resources that we could possibly muster, our robots, teleoperated or not, are still failing dramatically at performing even basic tasks. So putting aside the question of how does a robot do a fine motor manipulation task, how does a robot even get to the point where it could perform that task in a useful way? How does it get to the task it's trying to perform? I think this is actually a pretty major challenge. And I could watch these videos all day, but I'm going to kind of keep moving ahead for the sake of the talk timing. So I think that kind of illustrates that, at least for the foreseeable future, we're going to have humans in the loop in some capacity. Another way of thinking about this is if you reflect on what it would mean to actually take people completely out of the loop in a variety of applications, you realize there are a lot of situations where we definitely don't want to do that. Even if we were technically able, there are reasons that you can think of. We still want a doctor at the end of the day to be responsible for your surgery. You don't want to rely 100% on a machine. You want to have that human decision-making and competency behind it. Certainly in military interventions, we don't want to live in a world where machines are making decisions about who lives and who dies. And then from a broader societal perspective, even if we could replace workers in certain situations, there's significant value in having people contribute meaningfully to society. And so I think even putting aside the technical limitations that we currently face, I think there are legal, ethical, and political reasons or concerns that ensure humans will remain in the loop in a lot of situations for the foreseeable future. And so just return to this example one last time, the aspect of it that I want to emphasize is that when we have human cyber-physical systems, like we have in the case of robotic teleoperation, the key defining characteristic that you should keep in the back of your mind as I go through the talk is that there are fundamentally two decision-making agents that interact with each other through a dynamic world or a dynamic environment. And the key observation about this is that when you have two decision-making agents, you have the potential for asymmetry or incompatibility in aims or means of achieving a task. And so in fact, if you just naively sort of inject people into the presence of automation, or vice versa, introduce automation where there previously were only people interacting with simple machines, this can lead to performance degradation that can range from maybe mild loss of performance to potentially catastrophic outcomes. So there's a really well-known phenomena in the aerospace industry that's referred to as pilot-induced oscillations. And basically the idea is that due to the delays characteristic of human neurophysiology, you can take a perfectly well-designed aircraft that seems stable, it seems to satisfy some performance criteria in terms of maneuverability, et cetera. You can put a pilot in there who's highly trained, and just due to the fact that it takes time for the sensory data coming into their eyes to get processed by their brain and converted into neural commands that activate their muscles, that closed loop interaction between human and machine can lead to instability that can cause crashes of test aircraft. So this has actually happened several times. Most recently, I think it's called the X-2 fighter or something like that. The very first flight, the pilot had to abort and crash the aircraft, and the cause was determined to be one of these pilot-induced oscillations. And then something that we in the audience may have more direct access to in our daily life, I mentioned this Tesla software update where they turned a portion of their vehicles, the fleet of vehicles, into self-driving or semi-autonomous cars. So I'm going to show the video now. The video isn't, some of you may have seen this, the video is not fantastic quality, so I just need to set it up a little bit briefly. In the video, the car is driving itself, so the person's hands are not on the steering wheel. You can't see the whole steering wheel, it's kind of unclear. And so I just want you to see what, in this particular person's experience, happens when the car has control of the vehicle on a windy backcountry road where this system really wasn't designed to be deployed. So I think it takes a few viewings to really see what's happening here. This kind of went viral. You might have seen it on some blogs or something. Effectively, the car is following the road, and it's tracking that vehicle that's way up in the upper right corner. Right? It's trying to keep a respectable distance away from it. And then that vehicle gets obscured, maybe due to the lighting variations, et cetera, that are going onto the vision system in the car. And the car decides, oh, actually, what I need to be doing is either veering to the left to follow that car in the distance, or maybe it thinks that the oncoming car is actually the vehicle it needs to be following. And so it wants to turn in order to account for that. And you see that without the person intervening, there either would have been a head-on collision, or the person probably would have been run off the road, essentially, by the automation. And so the takeaway for me from this is that if we naively couple humans with machines, we can end up with a closed-loop system that performs far worse than would have been the case with either a human just driving the car on its own, or maybe a situation where only cars can drive themselves. So as engineers, we want the ability to, if we roll out a software update in our Tesla vehicles, we want the ability to guarantee that this closed-loop interaction between people and machines is going to be safe and is going to meet some performance criteria that we want to set. And so effectively, at a high level, in this sort of block diagram I've drawn here, we want to alter this sensorimotor loop. We want to intervene. We want to have the automation, the robot here, actually take measurements and make its own decisions about how to change the way the person's interacting with it to, it hopes, improve performance. But the key observation is that any intervention will fundamentally change this sensorimotor loop. And so without the ability to predict the consequences of our interventions, there's no way to guarantee safety. So the focus of the talk today is going to be developing predictive dynamical models for these sensorimotor loops so that ultimately we would be able to use them to implement provably safe interventions into human cyber-physical systems. So just to recapitulate this in a slightly different way, the talk will have two parts. The first will focus on developing predictive models for the way people control dynamical systems or machines. And the second half of the talk, it'll seem disjointed initially, and I'll bring it back together at the end. I'm going to talk about some of my work on developing better predictive models for how how robots interact with the physical world and the associated terra-dynamics. I'm just going to glance at my clock here to make sure I don't completely overrun the schedule. So to begin, I want to focus on modeling the way people interact with dynamical systems or control systems. And the launching off point for this, for me, this is largely the focus of my postdoc work over the past year. And the starting off point for me was, OK, there are a lot of really good scientists that have been thinking about this problem for decades. So let me dive carefully into the scientific literature and see if I can extract some overarching principles or paradigms that we might be able to do some engineering in. And there are many competing theories or paradigms that describe how humans control systems or how they synthesize volitional motor acts. But one pretty popular paradigm conjectures that we use in our brain, somewhere encoded somewhere in our brain, and there's a lot of debate about exactly where, exactly how, but at a high level, people say we have some models in our head of the world. And the models come in a couple of different flavors. So one flavor of model is a forward model that predicts the sensory consequences of our motor actions. So mathematically, the way this works is I apply some input U, so this would be like a neural signal sent to my muscle. And then there's some model M. This is like the plant dynamic if you're a control engineer. But basically the Lagrangian mechanics of my limbs moving in the world. And then there will be some output, and this could be like how close I'm getting to grabbing my water bottle so that I can take a drink of it, something like that. And then there's kind of another main flavor of model that's basically the opposite or the inverse of this forward model. What it does is it tries to compute or predict the action that's expected to yield a given desired behavior. So this model goes in the opposite direction in terms of a block diagram than the forward model. It takes the desired task as an output, and then by applying the inverse, we obtain an input that if we were to plug it back into our forward model, we would expect to give that output. And it's very popular in the motor control literature, the kind of theoretical and experimental neuroscience literature, to not use these models completely in isolation, but it's sort of natural to think of them as being paired. So I have a forward model that predicts the sensory consequences of my motor actions, and I pair that with an inverse model that allows me to go from task to action, essentially. And there's a lot of theoretical and empirical evidence that this is the most plausible arrangement of these internal models in people. And what I really liked in particular about this theory of internal models is that there's a really strong, at least mathematical and conceptual parallel in the engineering disciplines that I'm most familiar with and that I typically work in control theory, robotics, artificial intelligence, because we have theories of adaptive control, we have the internal model principle in control theory, and we have techniques for machine learning that really have a similar conceptual and block diagram flavor, but just cache them out formally in kind of different mathematical frameworks than the scientists typically work in. And so part of my task was to try to take, this is a very nice story to tell at an abstract level. It only took me 2 slides, and you probably pretty much completely understand the concept at this level of abstraction. But it turns out that there's a lot of difficulty in actually cashing out this theory and instantiating it in any particular, or operationalizing it in any particular context. So for instance, even if you think about the forward model, my world, in a lot of the papers I was reading, these models are treated as just static maps. They could be linear or nonlinear. A lot of times in the literature, just to make things easy, you treat it as linear, or you treat it as obtained from like a support vector machine so that, to estimate it, you just have to do some linear algebra. And that's convenient and that's nice, but from the perspective of ultimately I want to understand how people control robots, which are dynamical systems that have their own internal state, we need to think about a different class of forward model than had typically been treated in the literature. We need to think about a dynamic forward model wherein the output is not directly a function m of the input, but instead the output reads out from an intermediate state variable that could contain, for instance, the positions q and the velocities q dot of a bunch of limbs in a body. And that intermediate dynamical state is influenced directly by the input and evolves according to possibly second order ordinary differential equation. So in this dynamic setting, the key distinction is that the output is not directly a function or even directly influenced by the input. In order to go from input to output, you have to pass through a dynamical system. And so even once you've fixed and you've decided, OK, I've chosen my particular forward model, it's static or it's dynamic, whatever, there's still kind of a difficulty sometimes in practice in actually cashing out what you mean by the inverse model, or even obtaining a closed form expression or a computationally efficient means of evaluating the inverse model. So in the case of the static map, I think one thing that's clear is it would be hard to invert an output that is not achievable no matter what input you apply. So if the forward model M wasn't onto or didn't go, give you every single possible output available, then it would be impossible to invert any output that's not achieved. Another observation is that if two distinct inputs gave you the exact same output, it would again be hard to invert that output because there would be some ambiguity about which you should choose among the family of inputs that yield that output. So if the map, and this is true in the static or dynamic case, if the map fails to be one-to-one or onto, those are the mathematical properties I'm referring to for the forward model M, then it's tricky to think about how to invert the model. And in the dynamic case, there's even a little more difficulty that hinges on the existence of this intermediate state variable, where you might ask yourself questions like, well, does the output need to depend on the input in a causal way, or could it possibly depend on the values of the input far into the future? And another question is, well, there's this intermediate state. Does the output or to formulate the inverse, does one need to estimate the state of this dynamical system? Is that strictly necessary? When? Et cetera. And so then what I did was I kind of turned to the tools that we have in control theory, and I kind of took a fresh look at a pretty well-trodden area of mathematical control theory that turns out to give pretty crisp answers to the question of, given a particular class of forward models, what is the inverse? It gives us a really straightforward procedure to construct the inverse and interrogate it, look at its mathematical properties, and what implications that might have for the actual system we're interested in studying. So this is the first of two technical kind of deep dives that are going to take a few slides. If this is not your area, or if you're kind of tired this morning, you may just want to check your email, close your eyes for a few minutes. But for those that are interested, I wanted to give a little bit of the technical meat of the two contributions that I'm talking about. So if we start with a forward model, we're going to put it into what control theorists call control-affine form. This turns out to be not totally general. There are some systems that are not, you can't write them in this form, but it turns out to model a pretty broad class of systems, including mechanical systems like robots. And so that was my starting point, was that class of forward models. Then it turns out that by imposing a technical assumption, this is the most technically detailed part of the talk. The technical condition I'm using here, if you're a control theorist, you're used to doing nonlinear control, feedback linearization, the technical condition I'm imposing is strict relative degree. So this relative degree is going to be this parameter gamma you're going to see floating around in the talk. If you're not familiar with this area, gamma is just a counting number, 1, 2, 3, 4, 5. At most, it could be equal to the dimension of the entire state, which is n. But at the very least, it's going to be 1, but it's some number. And under this technical condition, and again, this restricts somewhat the class of systems we can consider, but it's easily satisfied for mechanical systems where I apply forces and then I measure positions. In that case, the relative degree gamma is 2, and that's kind of uniformly true. So I don't think this is a particularly restrictive condition, at least in the applications I'm interested in. Under this condition, we get kind of a remarkable result, which is that we can change coordinates. So we can just adjust our point of view on our system. We started with a state variable x, and we're going to now decompose that into a xi and a zeta. Xi is going to have dimension gamma, and that's our relative degree. That's that special counting number we're going to use a lot. And zeta is going to be everything else. And it turns out just by changing our point of view on the system, we can dramatically simplify our forward model. So what we end up with in the xi zeta coordinates is a forward model where zeta evolves in a nonlinear way that depends on xi and zeta, maybe in a complicated way. But you'll note zeta doesn't depend any longer on the input. So that's one simplification. And then the output is now just equal to, instead of being a nonlinear function of the whole state variable x, it's now just it's just the first component of the portion of the state xi. And then the xi dynamics are just a chain of integrators of length gamma. It's just gamma integrators winding up. So in a mechanical system, gamma is 2, and so we're doing 2 integrators. We're going through accelerations to velocities to positions. And then the dynamics of that gamma derivative of the output is just a scalar nonlinear differential equation. So now b and a are just scalar functions. They're not vectors anymore like they were in the original forward model. So this is particularly simple. And in particular, it lets us, so I talked here about the forward model. Now what I'm going to do is start from the simplified forward model and derive the inverse model. And it turns out in this particularly simple form, this derivation is one line. All you do is solve. I know that y equals xi1, and I know that the gamma derivative of xi1 is this scalar function of the input u. So if I just solve for u in terms of the desired output y, then I get an input that I can apply that depends on xi and zeta. That'll become relevant on the next slide. That's just a simple algebraic function of the gameth derivative of my output. And if I match the gameth derivative of my output, then I know that because xi, the dynamics of xi, just wind up through gamma integrators, that means the output is going to match the desired. And there's some technical issue here that, OK, if the initial condition wasn't exactly right, then I have to augment this with some feedback. That's just technicalities. That can be handled. The real key insight is that for this class of forward models, the inverse problem is solvable using simple scalar algebra. However, the solution, which is kind of forced on you. By the way, this inversion here for this class of models, there's no other way to invert the model. You have to match the gameth derivative of the output if you're going to match the output once it goes up through gamma integrators. And so the form of this input is actually forced on you by the structure of the dynamics. There couldn't be another input that would invert the system. So the important thing about that is that this input does something really funny to the closed. Once you close the loop with this inverting input, it does something funny to the dynamics. What it does is it gives us a system where the gameth derivative of our first state variable is just the gameth derivative of our desired output. And then these other excluded dynamics, I might refer to them as the zero dynamics, they have no influence on the input-output behavior of the system. And so formally speaking, once you close the loop, the states in this zeta vector, these zero dynamics, are unobservable. What this means is that I can't actually, in reality, using the outputs available from the system, unless I had some auxiliary way of getting the full state of the system, just using the outputs that I had available when I solved the inversion problem, I can't actually input the inverting input. The reason for that, if I jump back, that inverting input depends on the full state. So there's something kind of funny that happens here conceptually. I'm forced, the inverting input, if it's obtainable, is forced on me. The structure of it's forced on me algebraically. But if I actually close the system loop, I realize that I can't actually implement it in practice, in general. However, just kind of looking carefully at the dynamics of the system, what we realized is if we restrict the class of systems, of models or robots that we allow the person to interact with, in particular, if we assert that they have to be stable, both the forward and inverse model have to be stable, then it actually doesn't matter that the person can't estimate the full state. So the formal statement of this is if our forward and inverse models are stable, then you don't need to estimate the system state to invert the dynamics, at least asymptotically speaking. What you can do is, if you knew the system model, you could compute the inverting input from any initial condition, and then you could apply your inverting input using your forward model of the result of applying that input to the system, and that will asymptotically invert the original system's dynamics. It's a little bit formal and abstract, and so I want to kind of illustrate this with a cartoon. If I have a person controlling a complicated physical system, for instance, a humanoid robot, and if the person knows the model, they've developed it in their head, they have the robot's dynamics model in their head, and if that model pair, M and M inverse, are stable, then the person doesn't need to estimate the discrepancy in initial conditions for copy 1 of the subsystem or copy 2 of the subsystem. It never needs to estimate the real system's state, at least not the whole thing. What it can do is just simulate it, use an internal copy, I'm going to call that x hat, and that will cause all initial configurations of the robot to asymptotically move in sync and track what the person has in mind to achieve the task they're trying to perform. So just to restate this in slightly less formal terms, if you have a stable model pair, all trajectories asymptotically converge to what the person is trying to get the physical system to do in their head. And so in a sense, this feed-forward input, or this open-loop input the person is applying, asymptotically inverts the dynamics of the physical system. So with this tool in hand, now we have a characterization of the inverse model. If a person really does control a system by inverting its dynamics, we know what they're going to do, because we know the dynamics, and that forces the inverting input on the person. They have to learn that, and so we can predict what they're going to do. And so now we can invoke this in this intervention problem that I mentioned at the top of the talk. The basic idea here, I'm going to do it in formal details again and then show you a cartoon, is that if we observe the person controlling the physical system, at the beginning we don't know what they're trying to do, whether they're trying to go and screw in a light bulb or go and pick up a water bottle or go and eat some chocolate. But if we observe them performing their task, because of the structure of the model, we can infer their task. And the task here, eta, is just the output that we measure, so the positions of the robot arm, and then all of its derivatives up to order gamma minus 1. That's kind of a technical detail. Just think of it as we observe the person behaving, and from that we infer what they're trying to do. And then based on that, what's interesting is that though that task can then be injected into these unobservable zero dynamics that, again, have no influence on the input-output behavior of the system. So to the person, they're just sort of internal. They're not really relevant to the task they're trying to perform. And what's interesting, because this task now gets injected into these dynamics just become only dependent on zeta. They don't depend on the state of the rest of the states of the system. And so what the automation can do is solve a classical optimal control problem to improve the performance of the closed-loop system according to some criteria it has. So I just put a general performance criterion here, J. This could encode energy efficiency. This could encode time to completion. This could encode safety margin or safety factor or some other kind of quantity like that. And the point is that the automation can do something that automation is really good at doing, solving a fixed classical optimal control problem over a given time horizon. So this was a little formal. I want to recapitulate this in terms of the cartoon that I had at the beginning. Originally I observed that if we're going to intervene into a sensorimotor loop, that any intervention alters that loop, and so we have to be very careful to be able to predict the consequences of our intervention in terms of the closed loop performance. But the observation is that if the person is inverting the system's dynamics, so if all of those scientists have been right for 20, 30, 40 years, that the way people control physical systems, robots, et cetera, is to invert their dynamics, then subject to that assumption, intervening by the strategy that I just described is provably safe. I can guarantee that the closed loop performance will improve. So that's the main result that I wanted to talk about on how people control physical systems. I now want to switch gears and spend a little bit of time talking about my work on getting better predictive models for how robots interact with the world. Before then, we kind of take a step back and try to bridge those two topics. This part of the talk will seem dramatically different from the first part, but I promise you that they will come together at the end. So the initial observation that I want to make, if you haven't thought about this problem before, is that legged locomotion involves intermittent interaction with the world. Or you could replace legged locomotion with reaching and manipulating an object in the world involves intermittent interaction with the world. So in terms of how we model them mathematically and develop predictive models for that interaction, it's very different from if you've worked in hydrodynamics or aerodynamics of swimming or flying, where you're continuously exerting forces and continuously interacting with the environment. The point is that robots and animals doing legged locomotion or manipulating objects in the world interact intermittently. So we need new mathematical models. And so what I want to do is make two observations about this new mathematical paradigm or modeling paradigm of terra mechanics or terra-dynamics. I'm going to do them quick, and so I'm doing slides to highlight them really quick. You're going to immediately believe them. So I want to highlight that these are kind of non-obvious, non-intuitive observations. And then what I'm going to do is use them to derive some really interesting consequences for the way we should be building our robots to make them more predictable. So the first observation is that parsimonious or simple models for terra-dynamics are piecewise defined. I'll explain what that means in one slide. The second observation is that footfalls that happen nearly simultaneously, so when I reach out and I grasp, my fingers hit the water bottle at almost the same time. If I'm not a human, because humans kind of step 1 foot at a time, but if I'm an animal or a multi-legged robot, I generally have multiple legs hitting the ground or interacting with the ground at the same time. And that turns out to be a very key observation. So to substantiate this first observation, that simple models are piecewise defined, showing some snapshots here from some of the earliest work on high-speed videography. So you notice the year here. I mean, the book that I have is 1957, but the original publishing of this was 1887. Muybridge was a British scientist working in the late 19th century with early photographic technology and did some really clever stuff where he was able to set up a sequence of cameras, in this case, some 15 or 20 or something like that, and for the first time slow down natural motion to the point where we could actually start systematically reasoning about what's happening. And what I love about this is that I think it's really easy to imagine or see that when none of the limbs are in contact with the ground, the forces acting on the cat, in this case, are fundamentally different from when all four legs are on the ground. And really, it's different anytime there's one leg versus two legs, or really any subset of legs completely changes the continuous mechanical dynamics of the locomotor. So mathematically, the way we formalize this is we say, OK, there are some number n, just counting number n of limbs. And there are some internal position variables. I write my dynamics with respect to some angular variables or position variables or similar. And with respect to those parameters, the dynamics have the form, there's Lagrangian or mechanical dynamics, second order dynamics in terms of here are the applied forces. And then there's also some constraint forces that pop up. Because when I plant my hand on the ground and use it to leverage myself and push off, then my hand is not sort of penetrating the ground or oscillating between on and off of the ground at every time step of my simulation. It's really in continuous contact with the substrate. And so there's actually these hard constraints of that form, and those introduce Lagrange multipliers or constraint forces into our dynamics. And then the other key property of these simple models is when my hand hits the ground or my foot hits the ground, it's not truly the case that there's an instantaneous or a discontinuous change in the velocity of my limb. Right? Because in real physical reality, there's actually an electron cloud at the surface of my skin, an electron cloud at the surface of the ground or the tabletop. And when my hand gets close, then the electrons do some spooky stuff and start repelling one another, and I kind of perceive that as contact. But at the time, this all happens so quickly that at the time scales we're interested in, it's parsimonious or simple to just say, OK, when my foot hits the ground, there's a discontinuous change. Its velocity gets set to 0, and we move on from there. And so the dynamics that result are piecewise defined in the sense that every time a foot impacts, there's a discontinuity in state. And every time there's a different subset of limbs on the ground, there's different continuous dynamics governing the system's behavior. And you might think that this is kind of an obvious observation. I think it is. And that somebody really ought to have really formalized this and investigated the properties of these systems earlier. If you're having those thoughts, I agreed. But it turned out nobody had. And so we're in the process of really formalizing and investigating in a general way the properties of this class of dynamical systems in a way that would be accessible to the broader kind of robotics community. But with these two observations, the second observation that I want to make is that generally when animals and robots interact with the world, they are undergoing these instantaneous transitions or these collisions or these footfalls at almost the same time, or at least there are points in time where you get near-simultaneous footfalls. So one way of illustrating this is with some cockroach data. I worked on cockroaches as a graduate student. So here I'm plotting the fore-aft position of the tip of the foot in the center of mass reference frame. And you see there's kind of this pretty regular structure, and indeed, with respect to time. And indeed, if we just rescale the time axis using a phase statistic, which represents the percent progress through the stride or the step, what you can see is a really periodic structure where the transitions from moving your limb forward, swinging it through the air, to then plopping it on the ground and then moving it backward relative to your center mass reference frame, those transitions from moving up to moving down happen, these peaks coincide for triplets of limbs in the case of a cockroach. This is one way of illustrating this using data. Another way is just to watch a video. You might be more familiar with the idea that horses trot, dogs tend to canter, and any of these gaits, or horses do this as well, any of these gaits have multiple limbs, in this case the front left limb and the rear right limb, hitting the ground at almost exactly the same time. Right? And what's interesting about this, about the fact that cockroaches do this and quadrupeds do this, or horses do this, is that it turns out that a lot of robots people have built also do this. So I have here a video of a 6-legged robot doing its nominal gait, and a 4-legged robot from MIT doing its nominal gait. That was kind of inspired by dogs or antelopes or cheetahs, things like that. And they both have this property as well. So I have these two observations that the simple models we would want to use are piecewise defined, and in those models we will have multiple limbs undergoing these discontinuous transitions at almost exactly the same time. Now what I want to show is that the way that we traditionally build robots, because of the way we traditionally build robots, these two observations conspire to give us really pathological models that have very poor predictive power in physical world. And this is really an observation that's shown up a few different times in the literature. I'm just highlighting a couple of my favorite examples. So there were a couple of researchers in the mid-90s that realized that if I have a robot hand and all of the links are rigid, right? There's no compliance. I'm modeling them as like rigid metal beams. And then I grab a rigid object, for instance, and I'm holding on to it, and then another digit, another finger comes on to try to impact the rigid object. Then generally speaking, mathematical models that we have, the best models we have, will predict 5 different outcomes. And the outcomes depend on the instantaneous restitution law we use. And so basically it depends on whether you believe Newton or Poisson or Legendre or any number of other 18th, 19th century mathematicians and physicists about what happens when a finger impacts. And inexorably what happens is that my finger impacts and one of the 4 other digits has to pop off. That's the result in these couple of papers. That seems really non-physical. That's not what happens to me when I pick up my phone. Another observation in the case of locomotion, some researchers recently built a model of quadrupedal trotting. They wanted to model like a horse trotting. And what they found in their model, where again it had these rigid limbs, was that this model exhibited 3 distinct trot gaits. So they wanted 1, and they wanted it to be stable, but they ended up with 3, one of which had both limbs hitting the ground at exactly the same time, which is what we kind of mean by a trot. That one was unstable. And then there were 2 nearby ones that corresponded to the different sequence of first front and then rear limb hitting, or vice versa. And those were both stable. And they were all kind of nearby. And so what that means is that the system exhibited really extreme sensitivity to initial conditions, and it was hard to predict the outcome of an experiment. And so the takeaway is that we get inconsistent terra mechanics when we have rigid limbs. So then what I want to highlight is that if we just relax this assumption, we say, look, the real world is squishy, animals are squishy, a lot of legged robots have viscoelastic or series elastic limbs or actuators. And if we just relax that assumption, we actually remove this whole class of inconsistencies. And so if we have, in a parallel universes, we have a model with rigid limbs and we have a model with elastic limbs undergoing simultaneous or near simultaneous impact with their front and rear limbs. So we have some incoming velocity. The rigid limb model will predict, depending on which sequence of impulses you apply, first the front leg, then the rear, or vice versa, will predict different post-impact velocities. So you'll get this extreme sensitivity to initial conditions around the behavior that's ubiquitous and that you actually want to model. Whereas a model with elastic limbs, no inconsistency arises. The impulses commute in a mathematical sense, and so you can get a single well-defined outcome, and you can get better predictions. Then we started investigating this class of elastic limb models a little bit more carefully, and we realized there's actually a pretty interesting additional novel mechanism for stability that arises in them pretty much naturally. So in this elastic class of models with consistent terra-dynamics, and I'm just showing a video to kind of give you some visual intuition for what, okay, this model trotting along would look like. So now I'm going to look at this model in its state space. So I'm going to discuss this in a little bit of details to make the figure easier to understand. So I have the model. It has 3 position variables, the height, z, the horizontal position, x, and the pitch, or rotation of the body, theta. And then if I look at the trajectories in the model in the z theta coordinates, so height and rotation, I just forget about x for the moment, then I can see the different contact configurations. Here I have, in the blue region, I have the front limb on the ground. In the white region, neither limb is on the ground, and et cetera for the other regions. And the trajectory or the behavior I'm interested in is this one that goes straight down and has both feet touch down at exactly the same time. I'm just showing a snapshot near the touchdown event. And then you see that nearby trajectories kind of move toward it. So mathematically, we formalized this by kind of zooming in on this region and then thinking about, OK, if I were a little bit pitched up or a little bit pitched down, then mathematically what happens immediately after both limbs hit the ground? So let's just simulate or integrate the dynamics from a little before touchdown to a little bit after. And it turns out our finding is that if you have elastic limbs that are furthermore have some damping in them, so they're actually viscoelastic, then that kind of phenomena generally contracts your pitch angle near this simultaneous touchdown event. So not only do viscoelastic limbs give consistent outcomes or consistent predictable terra mechanics, they furthermore kind of have this novel passive stability mechanism that make it easier for you to actually get your robot to do that behavior. And then the other way that we've been thinking about applying these results is to try to synthesize dynamic gaits and maneuvers for our legged robots. So the state of the art is if you want your robot to do something cool and dynamic, like in that top video there, leaping up and grabbing onto a ledge, then what you do is you hire my collaborator, Aaron Johnson, to sit in your lab. You tell him the task you want it to perform. You give him your robot, and he sits in the lab for weeks doing experiments, thinking about it, tuning parameters, doing another experiment, going and getting dinner, et cetera. And he just iterates until he can actually get the thing to leap onto the box. And the problem with this approach, of course, is that then if we say, OK, well, that was nice, you leapt onto that box, what about this table, which is a different height and different geometry? Then he has to go through the whole process again. If we want to take these robots and put them into the real world and let people teleoperate robots that actually move around and interact with their dynamic environments in meaningful ways, we need robots that can automatically synthesize their behaviors. One way to pose this gate or maneuver synthesis problem is as an optimization problem. It's easy just to blithely say it. So I'm going to have some cost function or some performance criterion J that measures how well I leaped onto the box, how close I was to doing the dynamic maneuver I had in mind. And then the problem with this is that our dynamics are not classical. They're piecewise defined. They have these discontinuities. And what this means in terms of the math of the optimization problem is we end up with a mixed integer program, which is kind of generally intractable. There's kind of a combinatorial number of different modes we have to consider or possibilities we have to consider. And this problem is not actually solvable. But if we use the consistent and predictable terra mechanics that viscoelastic limbs just sort of naturally give us, this optimization problem turns out to become a non-smooth, so it's not as nice as if we just had hydro or aerodynamics interacting continuously with a fluid, but we can employ scalable algorithms. And I was actually super excited to learn that UW is actually kind of a center for non-smooth optimization. So I'm really looking forward to making some collaborators and connections in that domain. So now I've given you a little bit of a deep dive into these two topics I've been working on for the past year, trying to predict how people interact with dynamical systems, and then trying to make those systems more predictable and easier to interact with. And so now I want to conclude. I'm almost at the kind of cutoff point. So I just want to quickly conclude with a couple ideas about where I see this going in the future. To return to this teleoperation example, I do want to give a little credit to the successes of the DARPA Robotics Challenge. I don't want you to think that it was a total disaster. They actually did some really, really impressive stuff. And they were able for the first time to get semi-autonomous robots to egress or ingress into a building, pick up a tool, perform a task. And it wasn't just one robot that could do it, like dozens of them did it. This was really, if anybody was here a few weeks ago for Rust Headrake's talk, he was one of the teams that did very well, and he led one of the teams that did very well in the challenge. I mean, it was a phenomenal achievement for the field of robotics. But if you kind of focus on this last clip of this robot climbing up the stairs, and you imagine that it's a firefighting robot that needs to enter a building, go up the first 4 steps to get into the house, and you saw how fast or how slow it was doing it, right? How much they had to speed up the video to make this palatable to watch in a presentation. You realize that if you're the one trapped in the burning building, you don't want to rely on these robots anytime soon. And I think the way that we need to move this technology is we need to go beyond this sort of quasi-static, very careful, plodding interaction with the world, and we need to move toward dynamic telemanipulation, and a term that I almost was the one to coin, but there was a French tech report from the 80s that used it before me, dynamic telelocomotion of robots. So that's something that I'm really interested in working on. I'm also interested in continuing some work that I started at Berkeley on predicting how humans interact with machines and making it easier for robots to interact with humans and vice versa. And this paper that came out in IROS last year, or this year, had a really simple premise, which is that if a robot is going to hand something to a person, it's going to be easier if the robot knows something about the person. So if they have a personalized or an individualized model of that person's geometry, kinematics, constraints, if they have their arm in a sling, if they're tall or short, if they're et cetera, different variations. And what I think would be interesting to kind of extend this work going forward is to develop provably safe teamings of humans and robots. And then a final trend I wanted to highlight that's kind of a special focus both of my department and this campus is this problem of developing smart cities. And I see a lot of potential for developing safe, semi-autonomous robots and deploying them in these smart cities. I mean, we're not going to solve every single problem here, but we might be able to, kind of leveraging the partnerships that my chair has developed with Shanghai's Jiaotong University, we might be able to deploy these robots in the mobility or transportation sectors, in monitoring and maintaining buildings or other kinds of critical infrastructure. And I'm really excited about the potential of that area. So the concluding thought that I want to leave you with, returning to this illustration of these, what I'm calling these human cyber-physical systems now at the end, I think what's really interesting and exciting about this application domain is not that humans are treated as a nuisance or a disturbance to be rejected, as has happened in a lot of semi-autonomy research over the preceding decades. What I think is very exciting about this domain is the potential to leverage humans as the enabling technology to improve performance and yield really helpful engineered systems in society. So with that, I'd like to acknowledge the contributions of all of my collaborators on this work and the support I've received both institutionally and from funding agencies as a graduate student and postdoc. And with that, I'd be really happy to take any questions that you might have.
We do have time for a couple questions. I have one. So
Great.
if you think about the variety of robots that humans are able to teleoperate, ranging from very simple wheeled things to flying drones or whatever else is going on, how do you think people are thinking about that? Am I subconsciously building these very, very seemingly tricky, complicated physical models, or what's going on?
That's a really interesting question. I don't know if I have to repeat it, but I will. I will repeat it and kind of rephrase it anyway. So the question to me is, how will we be able to, or how will we be able to make meaningful predictions for how humans interact with the range of devices that we imagine, that we already kind of have available at the consumer level? You know, I have a new automobile that has some self-driving capability. Is the way I interact with that the same or fundamentally different from the way that I have my, in the Bay Area, there's a startup that makes these drones that follow you as you water ski or snowboard or things like that. So the way that I interact with that, is that different from the way a first responder might interact with a teleoperated robot firefighter or something like that? I'm sure that there's going to be variation, application-dependent variations, but what I think is really exciting is the potential that there might be somewhat of a unifying systems-level science, so that maybe I don't even know the exact geometry or morphology or capabilities of the robot I'm teleoperating or controlling, and the interface is presented to me in such a way that it kind of doesn't matter. It doesn't matter exactly how many legs it has, exactly how big it was, whether there's some wheels or tracks that it uses intermittently, or whether I hand off control from one robot to the next or something like that. The human might be able to execute the task, and the autonomy just facilitates it.
Cool. Other questions?
Yeah, please.
You told us about the feedback the human is receiving back, like a visual or, I don't know, any kind of sensor, but how's the haptic feedback going to be like in what do you foresee for the future?
So I'm going to kind of broaden your question a little bit as I repeat it. You know, what I specifically outlined in the internal models section of the talk is a way a person could use an output like from a visual display, so like the position of an end effector of a robot arm, to then learn how to control that arm even if it had complicated dynamics, or similarly a drone or something similar like that. But as the technologies advance and we're able to use not these sort of one-way, you know, visual feedback and then I apply some displacement on a joystick, as the technology has advanced to the point where I'm actually able to send and receive signals directly from my brain, or I'm in a continuous closed-loop coupling through a haptic interface with the robot, what happens? So my answer to this is I think these technologies are very exciting. I think the potential of haptics, brain-computer interfaces, augmented reality in the kinds of problems I outlined are tremendous, and I'm very excited to be working in this domain. I chose to just pick apart the simplest and sort of easiest domain that I could imagine working in, but I'm certainly interested in extending it to incorporate the kinds of technologies you're describing. I think it'll be difficult because I think so what you're describing with the haptics, there's an immediate problem that's already a closed loop. That's already a sensorimotor loop. So now you're trying to go in and intervene in that, but you don't immediately have a predictive model for that loop in and of itself. And so I think we're going to need new science and new engineering tools to tackle that integration. Yeah, Chet.
Fantastic talk, Sam.
Thanks.
So I like the fact that you're showing that with elastic legs, with elastic interactions, obviously smooths out some of those contact dynamics. So I wonder if you could talk a little bit about what the sweet spot is, and why aren't the DARPA Robotics Challenge contestants using elastic actuators? Sort of where's that tunable stiffness? Where's the trade-off?
That's really great. So the question is, or the observation is that I really kind of advocated for robots that are squishy or that have viscoelastic limbs as opposed to these rigid, hard pin joints and things like that robots are typically built. And in particular, the DARPA Robotics Challenge robots are built this way. And why did they go that route? Why didn't they build squishy robots, or where's the future there? So my personal opinion, this is not something I could completely substantiate, it's partly just speculation, is that part of the problem in the DARPA Robotics Challenge, part of the limitation was the use of these rigid robot technologies. The fact that so many of them struggled to even get to the task, even to locomote over uneven or soft compliant terrains to get to the task, I think is an argument that approach has limitations. Now, of course, there's a real technical problem with introducing viscoelasticity, which is that you automatically double the dimension of the problem. You automatically, if you had two rigid links interconnected with a rigid constraint, that's actually a simpler system in some sense. There's fewer degrees of freedom, mechanical ways in which the system can move, than if they were interconnected with a spring. And so it increases the complexity of the dynamics in some way, but my speculation, my hope, is that by showing that the predictive power of the mathematical models can far outweigh the hindrance of the additional complexity. Yeah, question way in the back.
Last one.
It seems that in the DARPA challenge, stability was a big issue. Is there a reason the robots so closely resembled humans as opposed to having multiple pairs of legs or tracks?
So there were kind of two parts to the statement. One was an observation and one was a question. So I'll immediately address the question first, because then I have something more to say about more speculative to say about the stability question. So why were so many of the robots humanoid in the DARPA Robotics Challenge? That was kind of a programmatic decision on the part of DARPA. They basically set up the challenge so that humanoid was the most logical and most obvious system to use. And in fact, they contracted with a company called Boston Dynamics that was since acquired by Google to build a particular humanoid platform that would be shared by a number of the teams. So they basically decided, I would say DARPA decided that humanoid was the way to go for their challenge. And then on this other side, that the observation that stability was a real problem for those humanoids, I think that's the case. And that it would have been, that they might have, part of the reason may have to do with the inconsistencies I highlighted that arise from rigid body terra mechanics. Part of the problem is if I have very rigid, stiff legs and I don't know the height of the ground and I'm standing on one foot and I push down too hard with the other foot because I think the ground is lower than it is, then that rigid impact is going to send a shock through my whole body and just send me careening over. And I think that's partly responsible for a lot of the blooper reel that I showed.
Thank you very much, Sam.